Greetings, if you look at this graph, it's a connected graph, one component only, doesn't have any disjoint sets within itself. Each vertex you can go over that graph over its edges to any other vertex somehow with some walk path. And it's also not directed, undirected, it doesn't have directions on its edges. And with that, we can have something called circuit rank. So a circuit rank is basically an interesting concept. So when we have a graph which contains cycles like this one does, it's not a tree because it contains cycles and it's connected, but it's not a tree because it contains cycles. So in order to make it into a tree/forest, in case there were more disjoint components of that graph, meaning that there would be this one and then out of it, not connected to it via any edge, some other graph that also perhaps has a cycle, then all that stuff can become a forest if we remove a certain amount of edges. But we have to know how many edges are necessary at minimum to be removed. And circuit rank talks exactly about that. So actually, for undirected graphs like this, we can directly calculate it by the amount of components we see, edges and vertices. There's a direct formula for it. So usually one can denote it with letter R for the word ranks. Also, circuit rank is what we're talking about. And that circuit rank says how many edges at minimum we have to remove from such a graph in order for it to become a tree, to remove all the cycles, basically. So it's calculated as follows. It's basically the amount of edges plus the amount of components minus the amount of vertices. So I use the initial letters for those three things. So amount of edges plus amount of components, this is just one component. So in total, in this whole graph, there's one component. Everything is connected into one component minus the amount of vertices. So let's see how many we have to remove from this one. Well, you can also visually see, because we have to remove at least one from this cycle, at least one from this cycle, and you'll see, do we need to remove more? With more complicated graphs, you actually need this. With this simple one, you might see it straight away by going over that graph. But let's calculate it in this systematic way. Edges, so we have 4, 5, 8, plus components is 1, minus vertices, 4 and 3. So in total, we have to remove 2 edges. And is that true? Probably yes, as we see. So the 2 edges, well, it is definitely true because this is a rule for it. And now we know, at the minimum, 2 edges have to be removed for this graph to become a forest. Well, a forest that has only one component is a tree. So because the forest is an extension of trees, 2 more components that are each tree. So anyway, now we know we have to remove at minimum 2 edges for it to become a tree. So we can remove, for example, this one and let's say this one, it doesn't matter. So with that, we've gotten to a tree. So we knew at minimum 2 edges have to be removed for it to become a tree. We removed 2 edges and now we see it's a tree. There's no cycles and it's a connected graph. So that's that. Now let's look at another example where it has more components than one. So let's say we have, again, some components. Each of them will be a cycle or contain a cycle. So let's say a bigger cycle this time. So like this. And next to it we have something like this. And now let's see. For the same rule again, circuit rank calculated directly from the amount of components, amount of edges, amount of vertices, and tells us how many edges in total have to be. This is one whole graph. This is not 2 graphs, but this is just 2 components of one graph. They're just not connected. There's no edge connecting the 2 components. So within that component, you cannot go into the other component. That's the idea behind component, by the way. So the rank, this is R, is going to be equal to the amount of edges again, plus the amount of components minus the amount of vertices. Just like before. It works just the same way if there's more components. So amount of edges in total, we have 3, 5 here, plus the amount of edges here. Well, and let's make this graph more complicated. Let's say we don't have just this, but we will have also this. Well, also this number will now change, so let's look at it again. So this is 5, but this is now 3, 4, 7. So in total it's 12 edges plus components. How many components do we have? Well, this is one connected component, this is one component, so 2. And remove from that or subtract from that the number of vertices in total. Again, from both of them, because this is all one graph. Just separate disjoint components. So 5 here, and then 3, 8, 11. So in total, how many edges do we have to remove from both of these for everything to become trees? So it's 14 minus 11, so that's 3. And we see that basically for each cycle of the cycles that we see within those two components, we have to remove one. So here I would remove any, it's very symmetrical. So now this becomes a tree, it's a path now. If we remove this edge, so that's one edge removed, and we know that we only have to remove two more. So we can remove this one. Now this part becomes a path already, and then perhaps this one. And now we see this is a tree and this is a tree. So we made it into a forest, and we knew how many edges have to be removed from that for that.